under, which can be solved using the process of counting non-negative integer solutions of an equation of this format. Yeah, we were doing problems of that. So remember the cookie problem. How did we solve this problem using this specific method where we count the number of non-negative integer solutions for this equation? First of all, we represented this problem using that given equation, right? So we had 4 different kinds of cookies, 4 different types of cookies. So where we have to choose 6 cookies. So the number of cookies you choose of the first type, if you represent that with x1, the number of cookies that you choose of the second type, x2, the number of cookies chosen of the third type, x3, and the number of cookies chosen of the fourth type, x4, then can we not say that the summation has to be equal to 6? You have to choose 6 cookies in total. And if you choose x1 cookies, x1 number of cookies of the first type, x2 number of cookies of the second type, x3 of the third, x4 of the fourth, the total number should sum up to 6, basically, right? We have 4 different types of cookies, so 4 x's here. x1, x2, x3, x4. So x1 plus x2 plus x3 plus x4 is equal to 6, where each of these x's represent the number of cookies chosen of that specific type. So this is the exact equation that we have here. And if we are able to count the non-negative integer solutions to this equation, that will give us the answer for this problem as well. Because the count of non-negative integer solutions of this, what is that? Basically, all possible combinations of the values of x1, x2, x3, x4, all possible combinations of the values of these 4 variables to sum up to 6. All possible combinations of the values, which give us this value at the end after summing up. So what does that give us? All possible choices, all possible ways to choose 6 cookies of these 4 types. Okay, so the number of non-negative integer solution for this equation, where n is equal to what, guys? Here in this equation, what is n equal to? What is the value of n in this equation? 4. Very good. 4. And r is what? 6. Yeah. 6. So n is equal to 4. 4 different types of cookies. So n is equal to 4. The number of cookies you have to choose is 6. So r is equal to 6. So n plus r minus 1. 6 plus 4 minus 1, which gives us 9. And then n minus 1, which gives us 3. So nc3 or nc6 for that matter would have given us the same result as well. Okay. Now, this problem fits under a certain definition, a different way of defining as well. You can define this problem in these 2 formats as well. All right. And why is that important? Why are we doing this? Why are we defining this same problem, which we have already solved, in these ways as well, so that when you have some other problem, some new problem later on at some point, it's possible for you to read that problem and be able to say that, okay, this specific problem fits this definition or fits this definition, or this problem can be expressed using this equation, an equation of this type. So I can use non-negative integer solutions to solve this problem. So why is that important? Because that is what we do here in counting, right? We establish similarity between different problems and try to solve them in the same way to make our jobs easier, all right? If you know NC3, if you know this equation, obviously you'll be able to solve this problem. But to get there is the important thing. In all of these problems regarding counting, in combinatorics, you see that the key part is trying to identify the method, or the key part is trying to identify, okay, this is the problem. What definition or what format does it fall under? কারণ প্রবলেমে তো ডিরেক্টলি বলা থাকবে না এটা পারমিউটেশনের প্রবলেম, এটা কম্বিনেশনের প্রবলেম, বা এখানে নন নেগেটিভ ইন্টিজার সলিউশন ইউজ করো. You have to be able to read the problem and then, okay, see that, all right, this problem fits that criteria. All right. For example, we say that if you have a certain problem where you have to count the total number of ways to put r indistinguishable objects into n distinguishable boxes. You have total number of r indistinguishable objects which you have to distribute or place in n distinguishable boxes. Yeah. You have total r indistinguishable objects which you have to place or distribute among n distinct or distinguishable boxes. In that case, the total number of ways to do that is n plus r minus 1 c n minus 1, the same formula that we've used so far. And you will see that this problem fits this definition as well. This specific cookie problem fits this definition as well. Here, for example, what are you doing? You can say that the 4 different types of cookies, when you're choosing the 4 cookies, let's say you have a tiffin box or something and there are 4 compartments there. And you have compartment 1 for the first cookie, 2 for the second cookie, 1 for the first type of cookie, 2 for the second type of cookie, 3 for the compartment 3 for the third type of cookie, 4 for the fourth type of cookie, right? So basically you have 4 boxes, 4 distinguishable boxes, because each box is for each type. Okay, so 4 distinguishable boxes. The first box for the first type, second for the second type, third for the third type of cookie, fourth for the fourth type of cookie. So 4 distinguishable boxes where you have to place these 6 cookies. These 6 cookies are indistinguishable. These 6 cookies can be of any combination. You don't know. এই 6টা কুকির মধ্যে 6টা কি chocolate chip নাকি 6টা is, let's say, oatmeal cookies. You don't know that. You don't know any of that. So these 6 cookies are indistinguishable. You don't know the definition of these 6 cookies, the identification. So these 6 cookies are indistinguishable. So basically you have 6 indistinguishable objects which you can distribute among 4 distinguishable boxes. All right. If you, let's say, place 6 cookies in the first box, it means that you have chosen 6 cookies of the first type. We can interpret it that way, right? We can also interpret it that way. Also, that's one combination then. The first box has 6 cookies, the rest of the 3 has 0, 0, 0. So 6, 0, 0, 0. 6 plus 0 plus 0 plus 0 gives us 6. So that's one combination. Let's say we place 3 cookies in the first box, 3 in the second box, and then we have what? 3 plus 3 plus 0 plus 0. That's another combination. So that's another way of looking at it. We have 6 indistinguishable objects, which are the 6 cookies, which can be placed into 4 distinguishable boxes. All right. So in that case as well, we'll follow the same formula. N plus r minus 1 c n minus 1, or n plus r minus 1 c r. Also, if you think about it, again, let's look at this problem from scratch, but we'll look at it from a third angle. First, we looked at it based on the explanation that's given here or the way we have solved it. And then we looked at the same problem using this angle, which gives us the same solution actually, and then another angle. All right. So counting the total number of R combinations with repetitions allowed from n distinct objects is n plus r minus 1 c n minus 1. All right. So far, the counting problems that you did regarding combination in basics of counting, no repetitions were allowed there. Remember? The combinatorics problems that we did in basics of counting, no repetitions were allowed there. And because no repetitions were allowed, we could use the basic formula of counting. Which one was that? N factorial divided by n minus r factorial multiplied by r factorial, right? However, if you have a certain scenario where you have to count the total number of R combinations from n distinct objects, however, this time repetitions are allowed, you can use the same formula. All right. Previously, we were counting R combinations from n distinct objects where repetitions were not allowed. For that, we had n factorial divided by n minus r factorial into r factorial, right? However, if repetitions are allowed, in that case, we use this formula. N plus r minus 1 by n minus 1, or n plus r minus 1 c r. All right. And you will see that you can also look at this problem from this angle as well. Think about it. The 4 different types of cookies that you have, you can say that you have 4 cookies to be exact, right? You have cookie A, cookie B, cookie C, cookie D. So A, B, C, D. These, let's say, are the four different cookies. A, B, C, D are the four cookies. You have cookie A, cookie B, cookie C, cookie D. I'm not talking about type now. All right, I'm not talking about type of cookie. I'm just talking about the cookie itself. Let's say the first cookie, second, third, fourth, where these four are different. These four are all different cookies. Aren't you basically counting all possible ways to choose 6 cookies from these 4 different cookies where repetitions are allowed? If you, let's say, choose 3 cookies of the first type, what does that mean? Basically, it means that you've repeated the first cookie thrice, right? You've repeated the first cookie thrice. Let's say these 4 different kinds of cookie. All right. Let's say it's chocolate chip cookie, it's oatmeal cookie, it's butternut cookies, and it's, let's say, coconut milk cookies. All right. So we have these 4. So if we say that we'll choose 3 chocolate chip cookies and 3 oatmeal cookies, what does it mean? We have repeated the chocolate chip cookie thrice. একটা chocolate chip cookie একটা distinct object which we have repeated thrice. Oatmeal cookie is a distinct object which we have repeated thrice. So basically you have 4 different objects, 4 distinct objects, 4 distinct objects from where you will choose 6 objects. 4 distinct choices, from there you have to choose 6 objects where repetitions are allowed. So from that angle as well, you can look at this problem and you have the same solution there as well. You are counting the total number of ways to choose 6 objects from 4 distinct objects where repetitions are allowed. Okay, so counting are combinations, basically 6 combinations with repetitions allowed from n distinct objects, that is 4 distinct objects. So n is equal to 4, r is equal to 6. So the same formula. Does it make sense, guys?
Yes.
Okay. All right. Let's say you have t-shirts of 3 colors: red, blue, and green. All right. You have t-shirts of 3 colors: red, blue, and green, and you have to sort them separately. You have to sort them out. All right. So if we say that you have in total, let's say in total there are 100 t-shirts here. All right. Let's say in total there are 100 t-shirts here. Can you tell me how many ways are there to sort these t-shirts? How many ways are there to sort the t-shirts? I mean, if you have red, blue, and green t-shirts, yeah, how many ways are there to sort 100 t-shirts from them? Think about the problem. You have 3 t-shirts of 3 colors.
The same formula, like n r minus 1, n minus 1
What is n?
is 3 and r is 10 probably.
We're choosing 100 t-shirts.
100.
100 to C2.
100? What? Sorry?
100 to C2.
102 C2. Yeah, that's correct. 102 C2. 102 C2. Yeah, that's correct. 102 C2 or 102 C 100. 102 C 100. Okay. So yeah, that's correct. So again, here as well, see that it's obvious that we'll use this formula because we're on this topic, but it also fits the definitions that we've discussed so far. All right. So you have to choose 100 t-shirts which are indistinguishable. We have to basically distribute these 100 t-shirts into 3 distinct boxes or 3 distinct colors basically, right? Red, blue, and green. 3 distinct colors, 3 distinguishable colors, that is 3 distinguishable boxes. You can think about it. You have to distribute these 100 t-shirts into these three distinguishable colors or these 3 distinguishable boxes. Also, you can think of it this way, that we have to choose 100 t-shirts from 3 t-shirts, red t-shirt, blue t-shirt, green t-shirt. এই তিনটা t-shirt থেকে আমাদেরকে 100টা t-shirt choose করতে হবে where repetitions are allowed. All right? So you have to choose 100 objects from 3 different objects where repetitions are allowed. Also, you can place it in this format as well, where x1 represents the number of t-shirts of which are red, x2 represents the number of t-shirts, let's say, which are blue, x3 represents the number of t-shirts, let's say, which are green. So x1 plus x2 plus x3 should be equal to 100. And the number of non-negative integer solutions to that equation gives us the answer to the question. So yeah, everybody gets it? Does everybody understand where we are at with these problems?
Yes, ma'am.
Okay, very good then. So let's move on. So look at this problem now. How many different strings can be made by arranging the letters of the word success? Remember, we had a similar problem previously in basics of counting. Yeah, this one. All right. We had to count all the different ways to come up with strings which contain these letters, all right? So for that, it's pretty straightforward. You just use permutation, all right? So PNR, as simple as that, or NPR, whatever you call it. Here as well, it's the same problem, right? It's the same problem where you have to count all the different strings can be formed by rearranging. Rearranging. See, the word is arranging. Arranging means ki order matters, right? So all the different strings, counting all the different strings that you can form by rearranging the letters of this word. So basically, order matters. So in case of, for combination, what do? For combination, we choose objects and we're done. For permutation, we choose objects and then the order in which we chose the objects is also important, all right? Here, they're saying all the different strings that you can come up with by arranging the letters, right? So here, obviously, order matters. So will we use the same method that we had here for permutation? Will we use PNR for this problem as well? Remember what the problem is. Counting all the different strings that you can form using the letters of the word success. So it's about rearrangement, right? So order matters. So will we use PNR here? What do you guys think?
I think yes.
No, miss.
Why yes, why no? Why do you think will you use the same method, first of all?
No, because of repetitions.
All right, yeah, that's correct. Very good. Because of repetition, we actually cannot use PNR here. Because remember, the basis of the formula of PNR was what? That no repetitions are allowed, right? Remember, once you chose the first position, you chose the object for the first position. Once you chose the object for the first position, then from n we went to what? N minus 1. So what does that mean? We are not having any repetitions here. That is one of the basic foundations of this formula. That permutations, yeah, fine, but no repetitions are allowed. All right? So see, for the first position, there were n ways. For the second position, there were n minus 1 ways. Why? Because the first choice cannot be repeated. However, in this problem, if you look at the word success, there are repetitions or objects, right? In success, Are all the objects in success distinct, guys?
No, ma'am.
No, they're not. So we cannot use the same approach here. So this is an example of a problem which looks very similar to a problem that you've seen before. But if you rush and use the same solution, then you'd be wrong. Okay? So we have to be very careful of problems which look different but have different solutions. All right? So we'll have those kinds of problems as well. First of all, you have to be able to identify the similarities between problems, and so in order to be able to solve them using the same solution or the same method. Also, sometimes you'll come across these problems where they look similar, but they're actually not the same problem. They do not have the same solution. Here, for example, we cannot use permutation, even though this is a permutation problem. This is very clearly, as clear as day, this is a permutation problem by arranging the letters of the word success. However, we cannot use permutation itself to solve this problem. Why? Because here some of the objects are repeated. S here is repeated. We have 3 occurrences of S, 2 occurrences of C. So S and C are repeated. So we cannot use the same approach here. So how will we do it? Actually, to solve this problem, we'll use combination and product rule. So this entire task of counting the different strings that can be made by rearranging the letters of this word, we can break down this task into 4 tasks. Right? Think before we get to that, think about it. Look at this specific word, this specific arrangement, AGA arrangement at the dekho. S here is in what position? Position 1, position 6, position 7. There are 7 positions here. That is 7 letters, right? So 7 positions. And S is here in 3 positions, okay? Position 1, position 6, position 7. So these are the positions of S. Now, can we not say that if we change the position, let's say 1, 6, 7 theke, I change it to 1, 2, 3. That is, S will be in position 1, position 2, position 3. Instead of position being right now here, S is in positions 1, 6, 7. If we change the position and say that S will be in position 1 and then 2 and 3, will it not give us a different string, guys?
Yes, ma'am.
Okay, good. Then if we change the position from 1, 2, 3 to, let's say, 1, 3, 4, now S will be in position 1, 3, 4. Again, will it give us a different string?
Yes.
Yes. So you see, by changing the positions of S, we come up with different strings. So first, what we'll do is here, the entire task will break it down, where the first task is choosing the positions of S. All right, choosing the position of S. By choosing the different positions, all the different possible positions of S, we can come up with different combinations of the string. All right. Now, next what I want you guys to think about is, okay, it's clear that we can choose different positions of S and that gives us different strings. However, fine. However, when you have chosen 3 distinct positions, 3 distinct position choose kara pore, if you rearrange the SS within these 3 positions, will it give us a new string? Let's say, for example, position 1, 6, 7 ache ekhane, right? So let's say we placed first in the position 1, SK first position 1 place column, then 6, then 7. If we rearrange within that, that is, we place S first in 7 and then in 1 and then in 6. That is, if we rearrange the SS within these same positions, a 1, 6, 7 er moddhe jodi S gulake amra, if we switch them around, will it give us a new string, guys?
No, miss.
No. Think about it. A first position e JS, 7th position e JS ta ache. Ei dutar moddhe jodi if we switch them, it doesn't make any difference at all. It makes absolutely no difference. Changing the first S with the last S. They are the same objects, so it makes no difference. So basically, we are choosing 3 distinct positions from 7 choices, 7 choices of positions. And once we have chosen, the order doesn't matter. The order of choosing the positions doesn't matter. You have chosen position 167. এটাকে 167 বলো বা 176 বলো বা 761 বলো, it's the same thing. All right? So can we not say that the number of ways to place S in this string is 7C3, because you have 7 choices to choose from, 7 positions to choose from. You have 7 positions to choose from. You have to choose 3 distinct positions from them. So can we not say that the number of ways to place S in this string is 7C3? Does it make sense, guys?
Yes, ma'am.
Okay. All right. In that case, let's move on to the next alphabet, which is repeated. C. All right. C we can see is repeated. Again, same thing. Here, C has positions 3 and 4. 3 আর 4 এর মধ্যে যদি আমি সুইচ করি, আমি যদি বলি আমি C এর পজিশন, আমি বলবো 3 আর 4 না, আরে C 3 4 পজিশন এর C আছে পজিশন 4 আর 3 তে. Does it make any difference? 3 4 and 4 3?
No, miss.
No, it doesn't. Again. Also, at the same time, if I change the position of C from 3 4 to 1 4, now if I say that, okay, I'll choose, instead of choosing 3 4, I'll choose position 1 and position 4. Will that give us a new string?
Yes, ma'am.
Yes, ma'am.
Yes, it will. All right. So what are we doing here again? We are choosing 2 distinct positions from 7 choices. We are choosing, we are counting 2 combinations from 7 distinct objects. So we have 7 distinct positions. From there, we are counting the number of ways to choose 2 distinct positions, okay, for C, to place C. So can we not say again that the number of ways to place C in this string is 7C2? Guys, can we say that?
No, ma'am.
Why?
Three spots were already taken by S.
Very good. Exactly. Very good. So before we get there, remember we have broken down this task. This entire task, we have broken it down. All right. The first task was what? Choosing 3 positions for S. In whichever way you do it, J 3 position you choose whichever positions you pick, those have already been taken. You cannot choose those same positions for C again. If you have chosen the first position for S, first position in this place, you cannot place C again, right? The same position cannot be taken by 2 different letters, right? A first position, if you place S in the first position, you can place C in the same position for the same string. Aki string A, you cannot place C in the same position, right? A position can be taken by only one string. So since whichever choice we make, S eর J choice, J position গুলো choose করলাম, the moment we are done with picking those positions, those are taken. We cannot place C in the same positions for a certain string. So basically, we don't actually have 7 options to choose from anymore, do we? We don't have 7 options to choose from. We have now 4 options to choose from. 7 less 3. So 4 options to choose from. So the number of ways to place C in this string, what is that, guys? The number of ways to place C. Sorry?
4C2.
4C2, yeah. 4C2, exactly. So the third task, similarly, is counting the number of ways that you can place U in this string. How many ways are there? First of all, U here, there's only one U. U isn't repeated. There's only one occurrence of U. So there is only one U here. So basically, we have to choose one position, one distinct position from a choice of how many positions?
2.
2 positions. Yeah, 2 positions. Because already 5 positions have been taken. All right. So we have 2 positions left. So 2 positions to choose from, and we have to pick one of these two positions. So for you, there are 2C1 ways to place you in this string. And once you've placed you, the only other choice is one position left, one option left for E. So 1C1, right? And also remember that for each of the ways to choose the positions of S, each of the 7C3 ways, for each one of these 7C3 ways to choose positions of S, there are 4C2 ways of choosing positions of C, all right? That is, by that I mean, dhoro, SK e tumi position 167 e choose korla. S এর এই তিনটা পজিশন, এই combination, S এর এই specific, এই একটা combination 167 for this specific combination of S, for this specific combination of position of S, how many options do you have for C? How many ways are there to choose a position for C? 4C2 for this specific combination. For a different combination, let's say S is in position 1, 2, 3, SSS. S is in position 1, 2, 3. For that combination, for that specific combination as well, there are 4C2 ways to choose two positions for C. All right. So for every single choice that you make for S, S এর যে তিনটা position choose করো, for every single one of those choices, প্রত্যেকটার জন্য you have 4C2 ways of choosing two positions for C. Okay. And for each one of those choices of C, you have 2C1 ways to choose a position for U. And for each one of those choices, you have 1C1 ways of choosing a position for E. So basically, product rule, okay? Product rule here, because এই প্রত্যেকটা choice 7C3 এর মধ্যে যে যতগুলো choice আছে, প্রত্যেকটা choiceের জন্য এতগুলো choice আছে. For the first choice that you make, ওটার জন্য you have this many choice. For the second choice, you have this many choice. For the third one, you have 4C2 again. For the fourth one as well, you have 4C2. So what do we have to do? We have to multiply, right? Because of that, we have to multiply. We have to do the product. We have to get to the product of this. So product rule here. So an entire task broken down into 4 individual tasks, where the number of ways to do the first task, for each of the ways to do the first task, there are a certain number of ways to do the second task. For each one of the ways to do the second task, there are a certain number of ways to do the third task, and so on. So product rule here. 7C3 multiplied by 4C2 multiplied by 2C1 multiplied by 1C1. Does it make sense to everyone so far?
Yes, ma'am.
Okay. So if you compute that, and if you apply the formula for combination, that is, you do, let's say 7C3 7 factorial divided by what, 4 factorial multiplied with 3 factorial, all right? And then you multiply that with whatever you get for 4C2 and so on. Before even calculating the factorial values, you will see that you will get to this format, all right? Some of the factorials will be canceling each other out, okay? 7C3, I won't demonstrate this in detail here. You can try it out in your spare time. But when you apply the formula for each of these combinations, you'll see that some of the factorials cancel each other out. And in the end, you get something like this. 7 factorial divided by 3 factorial, 2 factorial to 1 factorial, 1 factorial, all right? You'll get something like this, okay? And as you can see, again, we're not bothered about what the answer is, all right? I don't need to see if you can calculate the factorial, all right? So yeah, why we have represented it in this format, however, that is significant. এইভাবে কেন represent করেছি? Because we will again place this problem under a certain definition. That is, if you have any problem which fulfills a given criteria, you can follow the same approach. So here, see, how many objects are here in this string, guys? How many objects are here in this string in total?
7.
7, very good. We have 7 objects here. And we have to count the permutations of these 7 objects, right? Rearranging, right? So we have to count the permutation of, say, these 7 objects, where an object of the first type is repeated thrice, right? An object of the first type is repeated thrice. What is the first type? Type S. So we have 7 objects here. That's correct. But how many types of objects are here? If you can say that. Or in other words, how many distinct objects are here? A সাতটা object এর মধ্যে how many distinct objects do we have? Distinct.
4.
4. Very good. We have 4 distinct objects. So the first object is repeated 3 times. 3 factorial. The second object is repeated 2 times. 2 factorial. The third object once, 1 factorial. Finally, 1 occurrence of the fourth object, 1 factorial. All right? So that is the format. If you have to count the permutations of a certain number of objects, 7 objects here, where there are, let's say, k types of object. Here, there are 4 types of object. All right? So you will have the product of k types of factorial in the denominator. All right? So here there are 4 types of objects. So you see we have 4 different factorials here in the denominator, the product of 4 different factorials. And how do we get these factorials? The number of objects of the first type, the number of objects of the first type, or the number of times the first distinct object has been repeated. Here, S has been repeated 3. That's 3. So 3 factorial. The number of times the second distinct object, C, has been repeated twice. So 2 factorial. All right? Or basically, there are 2 objects of the second type. So 2 factorial. Right? Then 1 factorial, 1 factorial. When you have to count the permutation, then you use this formula. Okay? So 7 objects where there are 4 distinct objects, and the first object is repeated thrice, so 3 factorial. The second object C is repeated twice, 2 factorial. The third is repeated once, 1 factorial. The fourth is repeated once, 1 factorial. All right? Does it make sense, guys? The
Yes,
significance of this specific format. All right. So then this definition should be clear to you as well. Following the same idea, if you have n objects, if you have to count the total number of permutations, all right? A problem where order matters, arranging, so order matters. If you have to count the total number of permutations of, let's say, n objects, 7 objects here, and is equal to 7 here, you have to count the total number of permutations for n objects where there are, let's say, k distinct types of objects. All right, k distinct types of objects. Here we have 4 distinct objects, or 4 types of objects, 4 distinct types of object. S, U, C, E. All right, these 4. Where the first type has ni indistinguishable objects. The first type, the type S, has 3 indistinguishable objects there. All right. Type C has 2 indistinguishable objects there. These 3 S's are indistinguishable, right? These 3 S's. Is there any difference between the 3 S's, guys? No. They are indistinguishable. So if you have n1 indistinguishable objects of the first type, here n1 is equal to 3. n1 indistinguishable objects. So here we have 3 indistinguishable objects of type S. All right. So n1 distinguishable objects of the first type, n2 indistinguishable, n2 indistinguishable objects of the second type. Here 2 indistinguishable objects of type C. So n2 indistinguishable objects of the second type, n3 indistinguishable objects of the third type, and so on until the kth type. Here the fourth type, until the kth type, where there are nk indistinguishable objects of the kth type. Here there is only 1 object of the fourth type. So yeah, so then you'll have n factorial divided by n1 factorial multiplied by n2 factorial, n3 factorial, and so on until nk factorial, right? So that format as well. Whenever you have to count the total number of permutations of n objects where there are, let's say, ni indistinguishable objects of type 1 to type I, where I is within this range. That is n1 indistinguishable objects of type 1, n2 indistinguishable objects of type 2, n3 indistinguishable objects of type 3, n4 of type 4, and so on until NK distinguishable, indistinguishable, NK indistinguishable objects of type K. In that case, you can follow this format. Okay, and this problem also fits under this definition as well. Does it make sense, guys?
Yes, ma'am.
Okay, in that case, if it's clear, so let's say we have 6 awards where you have 3 awards of two awards of type 1, category 1, given to two awards category 2 given to another person. Right. If you have a problem like this, let's say we have 6 awards, all right? 6 awards where 2 awards of one category of one type is given to one person. Is given to one person, all right? Then 2 awards of category under category 2. 2 awards under category 2 are given to another person, all right? To some other person. And then 2 awards under category 3, 2 awards of type 3 basically is given to another person, right? Where the order in which the awards are being given out, je order e award ta deya hocche, that order matters, right? How would you solve this problem? Do you understand the problem? Do you guys understand the problem? We have 6 awards, right? We have 6 awards. We have 6 awards where 2 awards fall under one category, say category 1. 2 awards fall under category 1, which can be given to a person, all right? 2 awards under category 2, which can be given to another person, the same person, all right? I mean, like 2 awards given to the same person, and then 2 awards given to some other person, all right? Then 2 awards under category 3 given to some other person, where the order in which the awards are given is important, all right?
Ma'am, is it 6 factorial divided by 2 factorial into 2 factorial into 2 factorial?
How did you get there? That is the important question, all right? How did you get there? Yeah, yes, that's correct. Yeah, okay. The total number of awards is 6. That is the total number of objects is 6. And then, yeah.
The total of objects is 6, and then there are 2 awards of the same type of category from category 1.
Okay.
So first it's 6C2, and then since 2 hours are already gone, and then it is 4C2, and then 2C2. So 6C2 into 4C2 into 2C2.
Yes, that's correct, right? So the important thing here, first that you need to notice is order, all right? Order matters. So this is not a straightforward combinatorics problem. This is a permutation problem. However, this is also not a straightforward permutation problem because we have 2 awards under the same category given to one person. So even though order matters, if you see something like this, the order matters. If you say that, okay, this is just a straightforward permutation problem, you'd be wrong. Why? Because yes, fine, order matters. But if the 2 awards which are of the same category, of the same type basically, are given to one person, you're giving the 2 awards to one person. If you're giving the giving 2 awards to one person, in that case, would order matter? You're giving 2 awards of the same category to one specific person, all right? One person. So in that case, would order matter? No, it wouldn't, all right? The second scenario as well. 2 awards under category 2. So again, 2 awards under the same category, which are given to another specific person. So here again, even though they said that order matters, the order in which the awards are given out, that matters when you have a number of objects. You have a number of objects of the same type, and you're giving it to the same person. In that case, obviously order wouldn't matter. So you should be able to identify that. First of all, that this order word should tell you that this is a permutation problem. However, it's not going to be straightforward, because here, even though it's order, but for this specific case, if you break down this entire task into 3 tasks, giving out the awards under category 1, then giving out the awards of category 2, then giving out the awards of category 3, if you break it down that way, the number of ways to do this, think about that. Here, in this case, order doesn't matter for this specific category. Category 1 এর মধ্যে যে 2টা award আছে, if they're given to the same person, order doesn't matter. Okay? So the important things to notice here is the term order, that this is a permutation problem. However, the fact that it's not a straightforward permutation problem. And here, again, we have 6 objects. So n is equal to 6. We have 6 objects. And then we have n1 objects of type 1, 2 objects of type 1, n2 objects of type 2, 2 objects of type 2, n3 objects of type 3, 2 objects of type 3. So 6 factorial divided by n1 factorial multiplied by n2 factorial multiplied by n3 factorial. So 6 factorial divided by 2 factorial multiplied by 2 factorial multiplied by 2 factorial, like one of you said. All right? So that's that. Okay. So yeah. Is that clear, guys? Placing distinguishable objects into distinguishable boxes. Oh no, sorry. Placing permutations within distinguishable objects. Permutations, a problem for permutation. This is a permutation problem, yeah, but there are indistinguishable objects there. Permutations, but there are indistinguishable objects there. Whenever you have to count the permutations, but with indistinguishable objects, you have to see if it fits this format and then use the specific formula for that. Does it make sense, guys? Is it clear?
Yes, ma'am.
All right. So hopefully if this definition is clear, then any problem that falls under this definition, you can use this method to count whatever you're asked to count in that problem. All right. We can also use the same method for a different type of problem. Placing distinguishable objects into distinguishable boxes. All right. So this time we have distinguishable objects which will be placed in distinguishable boxes. All right. So previously, remember, we were talking about indistinguishable objects placed into distinguishable boxes. Now we're going to talk about distinguishable objects placed into distinguishable boxes. All right. So if you have n distinguishable objects which would be distributed among k distinguishable objects such that there are n1 objects in the first box, n2 in the second box, n3 in the third box, n4 in the fourth box, and so on until nk objects in the kth box. All right. In that case, we can say that the total number of ways to distribute the n distinguishable objects into k distinguishable boxes in this way is going to be this. Excuse me. Sorry. N factorial divided by n1 factorial, n2 factorial, n3 factorial, and so on until nk factorial. All right. So if any problem, you can say that there are distinguishable objects. First of all, you have to see whether there are distinguishable objects which can be distributed, which have to be distributed among distinguishable boxes. If you're asked to count the total number of ways to distribute distinguishable objects into distinguishable boxes, in that case, if you're given that there are n1 objects in the first box, n2 objects in the third box, and so on until nk objects in the kth box, then you can use the same approach. Okay. Let's look at this problem. For example, this is an exhibit for this specific definition. So we are asked to distribute 26 people among 6 rooms numbered 1 to 6. So since it's people, so obviously they're going to be distinguishable. 26 people. Since it's people, they're distinguishable, right? Guys, make sense?
Yes, ma'am.
Okay. And we have to distribute them among 6 rooms numbered 1 to 6. That is room 1, room 2, room 3, room 4, room 5, room 6. So are the rooms distinguishable? Guys, yes or no?
Yes, ma'am.
Yes, the rooms are distinguishable as well. So we have 26 distinguishable objects which have to be distributed among 6 distinguishable boxes. That is 26 people, distinguishable people, who would be distributed among 6 distinguishable rooms, such that 4 of these 26 people, that is 4 of these 26 distinguishable objects are placed in the first box. 4 of these 26 objects are placed in the second box. 4 of these 26 objects are placed in the third box. That is 4 people sent into room 1, 4 again sent into room 2, 4 sent into room 3. Okay. So n1, n2, n3 is what? n1 is equal to 4, n2 is equal to 4, n3 is also equals to 4. All right. And then 2 people sent into room 4. So 2 of these 26 objects are placed in box 4, right? So what is n4, guys? Remember this definition? What are we doing here? We have n distinguishable objects which have to be distributed among k distinguishable boxes. N distinguishable objects, 26 distinguishable people, distributed amongst k distinguishable boxes, 6 distinguishable room. So our n is 26, our k is 4. So we have n distinguishable objects, n distinguishable people, k distinguishable boxes, k distinguishable rooms. 26 people, 4 rooms. Okay?
We have 6 rooms right now.
Sorry, 6 rooms. Sorry, 6 rooms. Yeah, that's correct. Excuse me. Got it confused with the previous examples. Okay, yeah, 6 rooms. Yeah, that's correct. So we have to distribute 26 distinguishable objects into 6 distinguishable boxes, where ni of these n distinguishable objects, from these n objects, n number of objects theke ni objects are placed into ith box, box I, where I is within this range. That is n1 objects from these n distinguishable objects, say n number of object theke n1 object choose kore, you place them into the first box. You choose n2 objects and place them into the second box. You choose n3 number of objects and place them into the third box, and so on. All right. So here as well, aren't we doing exactly that? We are choosing 4 objects from these 26 options. We're choosing 4 objects, 4 distinguishable objects, and placing them into the first box. That is sending 4 people into the first room, 4 into the second, 4 into the third. So n1 is equal to 4, n2 is also equal to 4, n3 is also equal to 4. What about n4? Guys, what would n4 be equal to?
2.
Why?
Because we are sending 2 people to that room.
Yeah, so basically we are placing 2 of these 26 distinguishable objects into the 4th box. So yeah, that's correct. And then 6 people in room 5. So your n5 will be 6, and 6 people in room 6. So your n6 will also be 6. Okay. So what do we have finally? N factorial, 26 factorial divided by n1 factorial multiplied by n2 factorial multiplied by n3, n4, n5, n6 factorials. All right. So yeah. So you have 26 distinguishable objects, that is 26 people, which have to be distributed among 6 boxes or 6 rooms. You see, denominator, there are 6 factorials in total. So 6 rooms, where each factorial is gotten from where? How many of these 26 distinguishable objects, how many of these 26 you send into the first room or place in the first box, basically. All right. So yeah, any problem that fits this definition, you can solve it in the same way as well. Does it make sense? Yes? Any questions regarding this problem? Okay. I hope the silence means that all of you get it and not that you guys are totally, utterly lost. Okay, so that's all. We'll look at binomial coefficients in the next class. I would like for you guys to think about these problems and work with it a little bit, because some of you might be confused, all right, and not be speaking up right now. However, I must mention that it's very important that you guys speak up when we are talking about these problems, all right? As you must have seen in previous demonstrations of quizzes, that the problems in the exams and the problems in the assignments are a lot harder. So in order to be able to do those, especially in the exams, when you have to think on your feet, you have to absolutely make sure that you understand all of these concepts. All of these concepts are still clear, all right? So at any point, if you have any confusion, no matter how small or big, you should mention that, all right? Because if you don't tell me that you have a problem, I won't be able to solve it at all right? If you tell me, at least I can try. So yeah, if you have any questions or confusions, basically, please speak up, okay? All right then. Okay, so in that case, we can end the session here. We'll talk about binomial coefficients. We'll start talking about binomial coefficients in the next class. And before then, remember again, we have quiz 4 scheduled sometime this weekend, and we'll also have an extra class sometime this weekend. While we're on that topic, can I please get a quick vote